All right, in this video, we're going to begin section 13.7, which is tangent plane. And I'm going to insert a word in our title. This is not in the textbook, but we're going to also call these linear, which is really the important aspect. And I'll talk about that, why I'm inserting that in there. Linear approximations. And differentials. All right, so first, the tangent plane approximation of f at x naught, y naught approximates the function f for values near, for values x comma y near x naught, y naught, and is given by f of x, y is approximately f of x naught comma y naught plus f sub x evaluated at x naught comma y naught times x minus x naught, and plus f sub y evaluated at x naught y naught times y minus y naught. And your textbook writes this a little bit differently. They just write, they call x minus x naught, they call that h. So if you see this in your book, that's h, and this right here is k. Now, the reason I don't use that is just because you all are very familiar with the formula. It looks like this just from equation of plane. So I just figure we'll maintain that same notation with the x minus x naught. So this can also be rewritten as z is approximately equal to all of that. So remember, we use f of x, y, and z interchangeably. So if you want to write it with z instead, that's fine as well for this part right here. All right, so now what are we doing when we look at a tangent plane approximation? So given a surface f of x, y, if you're on the surface at a point near x naught comma y naught comma f of x naught comma y naught, it seems like you're on the tangent plane determined by x naught, y naught. And for this, you can see figure 13.41 on page 870. But if you just think of it intuitively, regardless of what the surface is or how complicated the surface is, if we zoom in close enough, and it's a smooth surface, if we zoom in close enough at any point on that surface, it looks like we're on a plane. And you all know this well from just living on the planet Earth, that when you look around, because we're so small in comparison to the Earth itself, when you look around, the Earth looks flat. But if you were to go to space or zoom out and look at the Earth, then you can clearly tell that the Earth is round. So if you are in close enough on any smooth surface, that surface looks like a plane. So we approximate things on a plane. Now, why do we do that? It's just a lot easier to work on a plane than it is on some arbitrary surface. So you think about measuring distances, because we're so close to the Earth and so small in comparison or relative to the Earth. We measure distances. We can measure straight line distances for the most part in things that we're doing that are, I mean, sorry, not straight line distance. Well, yeah, straight line distances, but distances like on a flat surface. We don't have to take the curvature of the Earth into account when we measure distances for the most part. Now, if you are measuring a long enough distance, then yeah, now you have to start taking curvature of the Earth into account. But it's a lot easier to do things like that on a plane, than it is on some arbitrary surface. So that's why tangent plane approximations are so useful and so powerful. And then I also mentioned linear in the title. So when we work with the tangent plane approximations, what we'll end up doing is that we get to use a linear function to approximate a non-linear function, or a planar function to approximate something that is not really on a plane. All right, so, and that'll be a little more apparent when I do some examples from the exercises. So consider a surface z equals f of xy. The differential dz represents the change in height of the tangent plane when x comma y changes from x naught y naught to x naught plus delta x comma y naught plus delta y. And is given by dz equals the partial of f with respect to x at xy times dx plus the partial of f with respect to y at xy times dy, where dx equals delta x, the change in x, and dy equals delta y, the change in y, the differential dz approximates delta z, the actual change in the surface height. And I'll sketch a little picture of this so we can kind of get a more clear understanding of what is being said here. So we had our set of coordinate axes. And so I'm going to sketch a surface, and I'm going to sketch a tangent plane, and then I'm going to kind of sketch a little box beneath that to kind of help us orient ourselves as to what's going on here. So try to sketch the same surface that I sketch normally. I would say it doesn't matter. Something may not matter what you sketch, but so, and it's going to be something simple. So we'll say whatever. It's just that'll be our surface, or a portion of our surface. And now we're going to consider the tangent plane to this surface. Now this surface will go on forever in every direction, but we're going to consider the tangent plane at that point right there. So the tangent plane at that point, at this point in the corner, would look something like this. So that tangent plane would go on forever as well, but we'll just draw that portion of the tangent plane. So to differentiate between the two, we'll put some little lines on our tangent plane. So now I've talked about this stuff in terms of dz, delta z, dx, dy, all of that stuff. So first, let's look at the point where we'll say we are on the surfaces right there. So directly below that will be the point. This will be the point xy. And then that would be, of course, be the point xy, f of xy. So then now what we're going to look at is we want to talk about some other point, x naught, y naught, that is near this point. So we'll put it, actually, let's do this. So we have some distance, we go in the y direction, say to about, we'll say right here, and we come to right here in the x direction. Oops, that didn't quite work out right. That's the distance we travel in the x direction. So this is our dy right there, and this would be our dx right here. So traveling from this point to this point, this point right here is x naught, y naught. So this is the change in y. This would be our change in x. Now, what we want to look at is what is, and remember dy and dx are the same as delta x and delta y. So this is our actual change. We're looking at being on our surface. So if we're on our surface, we were to move over this many units in the y direction, this many in the x direction, we will do that same movement on the tangent plane. That's why these are, those things are equivalent. But now our change in direction in the z is different than on the tangent plane than it is on the actual surface. So for the tangent plane, take this and move up. So our original height on the tangent plane was right here. So I drew that dotted line up there. That is our original height on the tangent plane and our original height on the surface. They are the same thing. So now, what about our new height on the tangent plane would be right here, and our new height on the surface would be up here. So those two are actually different from one another. So let's see if I can sketch this. This is supposed to be parallel to that. The line of draw is supposed to be parallel to that line down there, but it's not, because otherwise it's going to mess up our picture. So actually, let's just do this. So the change in z on the tangent plane will be that. From here down to that line, that's dz. But it approximates the change in height on this actual surface from, and this point, notice, is directly, that point is directly above that point. So the change in height of the actual surface would be, looks like about that. That's delta z. So we use, in going from, so say for instance, we are, and let me use the same points I use. So the change from some point x naught, y naught to a new point x naught plus delta x. So I probably should have called this one x naught, y naught, but, and then this one x naught plus delta x. But in our formula though, the dz is that the change in the tangent plane height, and it gives us approximation of delta z. So if you were asked for what is your change in height as you go from x naught xy to x naught y naught, what is your change in actual surface height, you use the tangent plane, use the differential, to approximate this change in height, because if we don't know that actual change in height, or if that's normally a lot more complicated to calculate than this dz is. So this is what we're finding, and what we're doing is actually approximating this height. All right, so I'll stop this video there, and in our next video, we'll do some examples of tangent plane approximations as well as differentials.